Hello, everyone, and welcome to our webinar today titled Cryogenic TEM for Battery Materials and Interfaces. Our speaker today is William Huang from Stanford University. William is a fifth-year PhD candidate at Stanford, working in the lab of Professor Yi Choi in Material Science and Engineering Department. There, his research focuses on using electron microscopy to understand the nature of solid-electrolyte interphase within lithium batteries. Previously, William earned a Bachelor of Science in Nanoengineering from UC San Diego. Next slide, please. If you have any questions during the webinar, please submit them using the question pane. We will try to answer them at the end of the webinar as much as we can. And if we don't get them during the time allocated to this webinar, we will make sure to get back to you via email in the next few days. So please feel free to submit your questions. And we will try to answer them as much as possible. I think that's all I wanted to say. Here is William for you. William, please go ahead.
All right. Thank you, Anna, for the nice introduction. Like Anna mentioned, I'm a PhD candidate here at Stanford University, and I'm going to be telling you all about some of my recent work using cryogenic transmission electron microscopy for the study of next-generation batteries. So batteries are extremely important for our clean energy future, especially for the decarbonization of the transportation sector through the electrification of personal transportation. And through that, that's the use of electric vehicles. And these electric vehicles can significantly reduce our carbon emissions, but the main barrier for their adoption is their lack of driving range. And that's coming from the relatively low energy density of the lithium-ion batteries used in most electric vehicles today. So in order to improve the energy density of lithium batteries within electric vehicles and increase their driving range and bring down ultimately the cost per kilowatt hour of energy storage, we need to look to new high energy density battery chemistries. And these are introduced mainly through changing out the materials within the battery. And just to make sure we're all on the same page, let's quickly review how a battery works. So a battery, a lithium-ion battery works basically by storing lithium ions between an anode, which is the negative electrode of the battery, and a cathode, which is the positive electrode. And basically lithium ions are shuttled in between a high chemical potential state, which is storage in the anode, and a low chemical potential state, which is storage in the cathode. And by basically shuffling the lithium ions between the high energy state and low energy state, we can store electrical energy and get it back on demand. Looking at the chemistry of the actual storage reaction at the anode, which is commonly made of graphite, we can immediately see where this relatively low energy density comes from. So in order to store one lithium ion, we need 6 carbon atoms in the graphite lattice, which means that there's a lot of dead weight in the battery. And basically to improve the energy density of the battery, we need to put more lithium ions into the anode. So just looking at this reaction, we can see that there are 6 carbon atoms that are being used to store lithium ions without really contributing directly to the energy density of the battery. Looking at alternative chemistries, we can immediately think of one that is very promising, and that's the lithium plating reaction, where we can remove all of that carbon, all of that dead weight, and basically store lithium ions in the form of elemental lithium or lithium metal. Looking at the actual capacities there, we can see that in terms of gravimetric capacity, we can store 10 times more lithium in the form of elemental lithium compared to lithium intercalated into graphite, which is a massive energy density improvement once we translate that to the full cell, where we can achieve close to 500 watt-hours per kilogram within the actual full cell of the battery, whereas a standard lithium-ion battery is about 300 watt-hours per kilogram. So this is obviously a very attractive technology. However, the reason why we can't really implement this at the moment is due to our lack of understanding of the lithium plating reaction and its dependence on what's called the solid-electrolyte interphase, or SEI. And this SEI is an extremely important structure within the battery. And it's commonly referred to as the most important and least understood structure within the battery. And this SEI is basically a surface layer that exists on almost every battery anode, whether it's graphite or lithium metal. And it's coming from the very high chemical potential of the anode. And what that results in is it will actually reduce the liquid electrolyte within the battery. The reduction of that liquid electrolyte will form a passivation layer on the anode that prevents the further decomposition of the electrolyte. And it takes this anode electrolyte interface that's normally thermodynamically unstable and actually passivates it and makes it metastable. So basically this SEI is going to contribute to the stability of the anode electrolyte interface, and it also will dictate ion transfer from the electrolyte onto the actual anode material. And this SEI dictates the performance of the battery. And to build better batteries, we need to really understand the structure and chemistry of this SEI. So people can build entire careers from the study of SEI. And people have been studying this since it was first proposed back in the 1990s. People generally think of the SEI as a surface layer on the anode. So they generally use surface analysis techniques in the literature to probe the SEI properties. X-ray photoelectron spectroscopy, or XPS, is commonly used because of its rich chemical resolution, along with pretty good depth resolution. However, it has pretty poor in-plane resolution. But using XPS, people have gained a lot of knowledge about the SEI, specifically what kind of components are within the SEI. And as this has led to this sort of conventional model of the SEI, which consists of inorganic lithium-containing compounds, namely lithium oxides, carbonates, and fluorides, close to the anode surface, along with more soft organic SEI components, such as organic carbonates, in the outer SEI surface, closer to the electrolyte. And a sort of bilayer structure of the SEI with an inner inorganic SEI and a more outer organic layer is commonly accepted within the literature. But this SEI, the in-plane heterogeneity of this SEI and its length scale is not really understood, namely because of the very large spot sizes used in most surface analysis techniques, such as XPS. In order to understand the distribution of these SEI components in plane, which is going to be very important for the actual SEI properties, ideally we would use a high-resolution probe technique, such as the transmission electron microscope, which can resolve heterogeneity down to the nanoscale. But of course, TEM generally involves very high energy electron beams, which can be a problem for battery materials. And the reason why that is because lithium compounds are generally very weakly bonded. And the second confounding factor is that lithium is very air reactive. So during transfer into the TEM column for standard TEM analysis, lithium will commonly react with the air and trace water vapor, resulting in corrosion of lithium into lithium hydroxides and lithium oxides. And that results in this very rough structure here from what was once a single crystal lithium filament. If you then attempt to perform high resolution imaging on this kind of lithium structure, you'll notice that you'll start to drill holes within the actual lithium material, coming from the beam damage from the very high kinetic energy of the electron beam. So this has been a major impediment to the high resolution study of lithium battery materials. In order to address this issue, our group, along with several other groups recently, have been inspired by recent developments in cryogenic electron microscopy, which recently won the Nobel Prize in Chemistry in 2017. And using cryo-EM, structural biologists can stabilize very sensitive soft molecules within the TEM for high resolution analysis. And those soft molecules are going to be much more sensitive than inorganic materials like lithium. And basically by freezing lithium under liquid nitrogen and using cryotransfer protocols adopted from structural biology it now becomes possible to stabilize lithium, elemental lithium, within the TEM without any air reaction. And that allows for atomic resolution lattice images of the lithium metal lattice, which has long been thought to be impossible. And this has been recently published by our group at Stanford, along with several other groups, including Shirley Mung's group at UCSD and Lena Korkoutis' group at Cornell. But more interestingly than just the lithium metal lattice, we can now actually image the lithium metal SEI. And this image here shows the lithium metal lattice interfaced with the surface layer, the SEI, and vacuum out here. And basically this SEI consists of crystalline components such as lithium oxides and lithium carbonates, that orange guy should say lithium carbonate, kind of embedded in a more amorphous matrix, which is presumably the soft SEI compounds. And if you compare this kind of picture of the SEI from high resolution cryo-TEM to this more conventional SEI model, where we think of this mosaic of different phases within the SEI, it looks pretty similar. We can see lithium oxides, lithium carbonates, along with the multitude of organic materials within this amorphous matrix. But if you look more closely, you'll actually notice some discrepancies. Namely, we're not seeing certain components within the actual experimental SEI shown in cryo-TEM compared to what we should be seeing based on XPS observations. And specifically, what we're looking for is this component, lithium fluoride. So lithium fluoride, it's just one component. You might be wondering how important this is. But if you're familiar with the battery literature, you know that lithium fluoride is an extremely important SEI component, and it's widely believed to be extremely important for the battery performance. So many groups, including our group, have basically looked to stabilize lithium metal along with other high energy anode materials, and have done so successfully by introducing more fluorine into the interphase. So many people in the literature believe that by adding more fluorine to the electrolyte, you generate more lithium fluoride in the SEI, which is thought to be very good for lithium metal stability. So the major question now for the entire battery field is, where is the lithium fluoride within the SEI? Why are we not seeing it with cryo-TEM? So to address this question, this brings us into the main motivation for this work I'm going to show you here. We want to figure out where lithium fluoride is. And in order to do that, we need to build a model electrolyte. So the SEI chemistry is going to majorly match the chemistry of the electrolyte within the battery. So we're going to use a common, well-understood, highly fluorinated electrolyte to investigate where this lithium fluoride is. So this is the electrolyte here. It's primarily a lot of organic molecules. So ethylene carbonate and diethyl carbonate are common lithium-ion battery electrolyte solvents. But this fluoroethylene carbonate, or FeC, is an extremely important electrolyte additive. And through the defluorination of this fluorine group, shown here, more lithium fluoride gets introduced into the SEI, which is commonly attributed to the stabilization effect of this electrolyte additive FeC. And you can see here in this Coulombic efficiency plot, where higher is better, by adding simply 10 volume percent of FeC into the electrolyte, the battery stability is greatly improved. If we then take this kind of, if we take lithium metal plated within this electrolyte, take it apart for standard ex situ XPS characterization, the same way everyone in the field does it, and start to depth profile, what we see is that the SEI structure looks a lot like what we would expect, and has been reported in the literature. Basically, there's an outer, more organic layer consisting of organic fluorines along with various carbonaceous materials, and by depth profiling deeper, we can see an increase in the lithium fluoride signal. So the SEI is getting more inorganic. And this would lead you to believe that the SEI has this kind of structure here, where the lithium metal surface, the actual anode surface, is interfaced with that inorganic layer I described earlier with lithium fluorides and oxides, and a more organic layer on top of that, that sort of bilayer structure. Then, if we take a similar sample of lithium plated within the same electrolyte, take it into the cryo-TEM, we can see that the SEI picture here, so lithium will plate naturally as these kind of nanowires or filaments. In the field, we generally call them dendrites, although they're not technically dendrites. But it naturally grows in this kind of beam transparent structure. you don't have to do any fancy sample preparation to get this nanoscale electron transparent material. And by looking at the SEI, we can see that it consists, as we observed before, of oxides and carbonates embedded in an amorphous matrix with lithium metal down here, vacuum out here. And looking at the Fourier transform, we can see that there is crystalline lithium oxide, but there isn't really any crystalline lithium fluoride within this image. But of course, this mode of high resolution imaging is a relatively is sensitive to only crystalline phases, and we're probing a very small area of the actual material. So in principle, if lithium fluoride were amorphous, we would not be seeing it in high resolution imaging. So we can take advantage of the rich spectroscopic capabilities of the TEM and use scanning TEM coupled with electron energy loss spectroscopy, all done cryogenically to mitigate beam damage, to see if we can detect any fluorine signal across a larger section of this lithium filament. And basically through this kind of cryo-STEM EELS mapping, we can see, first off, we're getting very good detection of lithium and oxygen, namely because, well, of course, there's a lot of lithium in the sample, but also EELS is very sensitive to light elements such as lithium, oxygen, and fluorine. We have a very rich lithium core coming from the lithium metal, along with a very rich oxygenated shell coming from that SEI. But what we're not really seeing within the SEI is any fluorine, which is quite surprising considering the 10 volume % of the fluorinated ethylene carbonate additive that we've added to the electrolyte. And basically, from this kind of observation, we can tell that the fluorine concentration in the SEI is actually very low. So we're not really seeing this sort of inner, more inorganic SEI close to lithium surface that we're observing from XPS. So what's going on? Well, based on this observation, we're not really seeing any of that lithium fluoride in that compact SEI layer that's on the lithium surface, but we are seeing lithium fluoride in the XPS. So lithium fluoride must be somewhere else. So the question then is, could the lithium fluoride be depositing outside of that compact SEI layer on the lithium metal surface? So to probe this, we thought of this experiment where basically we can produce a model SEI on a very low surface area substrate. Previously, we were looking at a high surface area lithium deposit, where we're getting all these nanowires plating out of a TEM grid. But here, by using a carbon film, a standard carbon film TEM grid, where you just have a flat conductive surface, carbon membrane on a TEM grid, we can generate this low surface area model SEI and probe a large surface area to look for fluorine. And basically, by forming an SEI on this carbon film TEM grid in a standard coin cell, and then performing STEM EELS mapping, we can see actually that there is a lot of particulate type SEI coming down onto the carbon film surface. And these SEI particles are very rich in oxygen along with fluorine. And looking closer at these fluorinated particles, we can confirm they are lithium fluoride, but actually they have a very interesting nanostructure as well. So if you look at the oxygen map coupled with the fluorine map, you'll find that a lot of the oxygen is coincident with the fluorine particles. And looking at a higher resolution scan, we can see that there's this sort of bilayer core shell type structure to these SEI particles, where the core is highly fluorinated, but there is a more oxygenated shell around them. Through looking at the actual EELS spectra of the fluorine particle, we can see that it matches very well with a lithium fluoride reference, confirming that these particles are in fact lithium fluoride. But they are covered in an oxygenated shell that consists of both lithium oxides and organic carbonates. And what this means is that these bilayer particle structures can actually give rise to what you're seeing in XPS, this sort of a bilayer, more organic, inorganic SEI structure. Through XPS matches this kind of SEI structure here on these particles, but it is not really what we see in the actual compact SEI film on the lithium surface. And if we look at the TEM of these actual SEI particles, what we see is that kind of interesting. We can first further confirm that these particles are in fact lithium fluoride based on the electron diffraction The reflections match well to the lithium fluoride 200 reflections. What's kind of interesting is that the lithium fluoride particles are textured. They have a preferred orientation, but are not quite single crystalline. You can see that here. The lithium oxide is polycrystalline, and there's also a lot of amorphous material as well, presumably the organic carbonates we're seeing in the STEM EELS. And if we then think back to the lithium metal surface, which is very high surface area, we can then imagine that the lithium fluoride particles probably do exist on those surfaces as well. But based on the very nanoscale heterogeneity we saw previously, where these kind of particles are precipitating over hundreds or over tens and severals of microns, rather than at the nanoscale, we can imagine that these lithium fluoride particles become very dilute once we take this to a very high surface area lithium metal deposit. And if we map enough of these lithium metal filaments, we can see actually that there are in fact some lithium fluoride precipitates coming down on some of these lithium metal surfaces, but they are very dilute, and they are precipitating outside of this compact SEI film on the lithium metal surface. And basically, from this study, we can show the power of cryo-TEM and the shortcomings of standard SEI analysis techniques used in the field, such as XPS. And basically, the problem arises from the large spot size of XPS. Through standard surface analysis techniques, we can get this depth structure of the SEI, but that does not really match the in-plane nanoscale heterogeneity that we're seeing through high-resolution probe techniques such as cryo-TEM. From XPS alone, we are deriving SEI structures that are not quite accurate for what's truly going on within the very complicated battery system. But using cryo-TEM, we can actually resolve the nanoscale heterogeneity within the SEI and show the phase separation between the lithium fluorides and other inorganic materials within the SEI compared to the very compact SEI film that's coming down to passivate the actual lithium surface. And basically, this compact SEI, the one that's actually covering the lithium surface and passivating most of the surface from further electrolyte reactions, is going to be what's truly dictating the passivation properties of the SEI along with the ion transport onto the electrode material. And components like lithium fluoride may or may not be as important as previously believed, and that requires further investigation. But basically, from this kind of study, we can see just how important high-resolution microscopy is for understanding what's happening within the battery. So lithium metal is, of course, very promising and very interesting for battery materials, but it's not the only promising next-generation battery material. Lithium metal is still a long ways away from practical implementation, and the next step within high-energy batteries is silicon anodes for next-generation lithium-ion batteries. And these silicon anodes are very attractive due to mainly their low cost. Silicon's extremely abundant in the Earth's crust, along with their high lithium storage capacity. So if you've been paying attention to the battery world and watched Tesla's Battery Day presentation, you saw their announcement of Tesla Silicon, which is their proprietary silicon technology that allegedly can bring down the dollar cost to $1.2 per kilowatt hour of energy storage. And this is very exciting and very attractive if you look at the silicon lithium alloying reaction. So up here again is the standard lithium intercalation into graphite reaction, where we're storing one lithium ion for every 6 carbon atoms. And down here is the silicon alloying reaction with lithium, where we can store almost 4 lithium ions for every single silicon atom. And through this kind of reaction, you can see just how much the capacity, the storage capacity of the silicon anode can compare to graphite, where we are also getting almost 10 times the storage capacity, the gravimetric capacity compared to graphite in silicon. But this very high lithium ion storage capacity also introduces the problems of silicon. Namely, because we're putting so much lithium ions into the silicon lattice, we're causing this 400 volume % expansion of the silicon structure. What this means is that, excuse me. What this means is that the SEI layer on the silicon gets fractured and broken as the battery cycles. And basically, new SEI will continue to form, and this SEI layer is going to consume lithium ions, trapping them irreversibly. So in short, your battery can store more lithium ions and have higher capacity, but the capacity will fade very quickly. So in order to understand silicon and its dynamic SEI behavior and try to create a practical silicon anode, we need to gain more insight into the silicon SEI properties and figure out how to stabilize it. So this is an opportunity for microscopy to understand this nanoscale silicon SEI. But this introduces its own challenges. Basically, in order to understand the silicon surface, we need to have the first thing we need that's requisite for all TEM studies is we need an electron transparent, clean silicon surface to study. In XPS and X-ray and SIMS studies of the silicon SEI, silicon wafers are commonly used due to their flatness and cleanliness, but that's obviously not practical for TEM because we need electron beam transparency. So to get around this, we kind of looked to what we previously did with lithium metal, and we actually grew silicon nanowires on a stainless steel TEM grid mesh. And basically, these silicon nanowires, they provide electron transparency, and they're also very high quality. They're single crystal with a thin native oxide layer shown here, but they also have direct electrical contact to the TEM grid. In real battery electrodes, the electrodes are a very complex composite of polymer binders and carbon additives, but by doing this kind of experiment, we don't really need any of those confounding factors such as binder and those additives. We also don't need to do any complicated sample preparation, such as using focused ion beam or microtomy to section a thin film electrode, which would possibly introduce sample preparation artifacts. Taking the silicon nanowire TEM grid, we can use this grid as a working electrode and lithiate it within a coin cell. Now, the second challenge of doing cryo-TEM on this kind of lithiated silicon nanowire is that lithium silicide, the lithium silicon alloy, is of course very beam sensitive due to the very high amount of lithium in the structure. But using cryo-TEM, we have already addressed that, and that won't present a challenge for further analysis. So taking that silicon nanowire TEM grid, fully lithiating it within a coin cell, we can then perform the same cryotransfer procedure, put it in the TEM, and do high resolution analysis of the lithium silicide SEI. So this here is the first image I've reported of lithium silicide in high resolution at cryogenic temperatures. And we can see that this core down here is crystalline lithium silicide, this Li15Si4 phase, which corresponds to the 3.75 lithiums per silicon atom. So the most charged state of silicon. Out here is vacuum, and this layer in between is the SEI of lithium silicide, which is what we, of course, truly care about. And this is lithiated in a standard lithium ion electrolyte, that ethylene carbonate diethyl carbonate blend, without any fluoroethylene carbonate. If we look at the EELS spectra, we can see that lithium is indeed preserved from this kind of cryo-TEM procedure. We get this very nice lithium K edge in the lithium EELS. But if we were to perform the same experiment, attempt to do room temperature TEM of lithium silicide, we would actually eject all the lithium out of the silicon nanowire. So looking at the SEI, which is what we really care about, we can see the sort of bilayer structure in the SEI. Down here, closer to the lithium silicide core, is a more amorphous layer consisting of organic carbonates, so the organic electrolyte decomposition products, along with the lithiated silicon oxide. So that native oxide on the silicon is actually electrochemically active and can be lithiated into lithium silicate, which is generally thought of to be an amorphous product, and that's what it looks like from here. On the outer surface, there is a lithium oxide layer coming from electrolyte decomposition as well. If we then delithiate that same sample, or a similar sample, what we see actually is quite surprising. So first off, the lithium silicide will delithiate, resulting in amorphous silicon. And that's well known to happen in the literature. Generally, after the first lithiation, the crystalline silicon structure is destroyed, and you're only left with amorphous silicon. Looking at the SEI, we can see that there isn't really any crystalline structures within the SEI. That lithium oxide layer in the SEI is actually gone now, which suggests that lithium oxide in contact with silicon is reversible, at least on the first cycle. And that is quite surprising and starts to suggest a very dynamic behavior of this SEI layer on silicon. Now, of course, in this image, we can see those two main observations, but because I mentioned earlier, this high-resolution TEM analysis is mainly sensitive to crystallinity. So we're not really getting all that much information from this image alone. But if we go back to the spectroscopic abilities within an analytical TEM, we can use techniques such as cryo-STEM EELS to gain more chemical information of the lithium silicide and its SEI. So going back to the fully charged sample, we can perform STEM EELS mapping, and what we see is that there is a lithium-rich core corresponding to lithium silicide, along with a lithium-rich outer shell corresponding to the SEI components. And that's not really too surprising there, but we can see that there is actually a dip in the lithium intensity between the core and the shell. And that's likely coming from the lithiation of the silicon oxides into lithium silicate, which is a relatively lithium poor structure compared to lithium oxides and lithium silicide. Silicon is, of course, enriched in the core, but we're also seeing a lot of carbon and oxygen in the outer shell. And that's corresponding to the SEI components along with the lithiation of the silicon native oxide. Looking at the delithiated sample, what we find is actually quite surprising as well. Not only is the lithium oxide reversible, so the lithium oxide is getting oxidized away, but the lithium itself within the SEI is mainly gone. We're not really seeing any lithium remaining on the delithiated silicon nanowire. Carbon is much more dilute, but the oxygen layer is still there, corresponding to the native oxide on the silicon. And basically from this, these two observations, the HRTEM along with the STEM EELS, we can see that there is some partial reversibility of the SEI on silicon, at least on that first cycle. Now, of course, in real silicon anodes, we wouldn't be using that standard ethylene carbonate blend alone. In all lithium-ion batteries, the stability of the actual battery chemistry is extremely dependent on electrolyte additives, such as that fluoroethylene carbonate that we talked about earlier. And FEC is known to be very good for lithium metal, but it's known to be extremely important for silicon anode stability. These cycling curves here show the rapid capacity decay, this blue curve, which corresponds to the left axis, the capacity, the right is the Coulombic efficiency. The rapid capacity decay of silicon in an FEC-free electrolyte, so just the ethylene carbonate alone. But by adding 10 volume% of FEC, the capacity retention is much improved along with the Coulombic efficiency. So that increases the lifetime of the battery significantly. But what's interesting is that by adding that 10 volume% of FEC, the first cycle efficiency of the battery of the silicon anode is generally reduced. So we can get more lithium back on the first cycle without FEC than with FEC. So that's kind of an interesting discrepancy right there. But generally, or more importantly, what we want to know is what exactly is FEC doing to the silicon anode and how does it contribute to its stability. So these images here are that the silicon nanowire TEM grid sample lithiated in an FEC containing electrolyte. So that same ECDEC with 10 volume% FEC. The silicon lithiates similarly. We still get this crystalline lithium-15 silicon 4 phase coming out in the silicon nanowire core. But then looking at the SEI, we can immediately see a difference. So previously in the FEC-free electrolyte, we had an SEI that composed of both amorphous components, such as organic carbonates, along with the lithium oxide. But here in this SEI, with the addition of FEC, the SEI is completely amorphous. And that suggests that the lithium oxide is mainly coming from the presence of the ethylene carbonate, whereas with the addition of FeC, the FeC will decompose first, reducing the decomposition of the EC. Now on delithiation, silicon and its SCI remain amorphous. That's not too surprising there. If you kind of squint closely, you can see that there does appear to be a low density surface layer, or a contrast difference between the amorphous silicon and this SCI layer. But that's not really super convincing just from the HRT-EM image alone. Going back to the STEM EELS, we can see that in the lithiated state, that lithium silicide nanowire looks fairly similar to what we saw in the electrolyte without FeC. We still have that lithium-rich core and the lithium-rich SCI, along with that intensity dip corresponding to the lithium silicate. Silicon's rich in the core, and then carbon and oxygen are both rich due to the electrolyte decomposition. But on delithiation, this is more interesting here. But basically, we can see that in the delithiated state, there remains a lithium-rich outer layer on the silicon nanowire surface, along with a carbon-rich layer as well. And that suggests that the FeC-derived SCI is actually electrochemically and mechanically stable on the silicon surface on that first cycle. And just for comparison, here is the same, here's the delithiated sample in the FeC-free electrolyte. With just ethylene carbonate alone, the lithium and many of the organic components are unstable during delithiation, whereas with the addition of FeC, those components are much more stable, and they actually remain persistent on the silicon surface. Looking at the actual EELS spectra, we can see that in the ethylene carbonate only electrolyte, so without FeC, in the lithiated state, which is the blue curve, there is a rich carbonate peak, or a strong carbonate peak, and that's coming from the organic carbonates depositing out of the ethylene carbonate. But on delithiation, those organic carbonates appear to be the reversible component, which is why the carbon and lithium intensity decreases on delithiation, instead leaving mainly olefinic carbon groups, which are going to be more insulating to the to ionic transfer between the electrolyte and electrode. In the case of the fluoroethylene carbonate containing electrolyte, they both contain strong carbonate peaks, and that carbonate peak is very persistent even on delithiation. And that's likely coming from the rapid defluorination of the FeC and its subsequent polymerization into a polycarbonate type structure on the silicon surface, which is generally thought to be a vinylene carbonate or VC type polymer. And basically, all of this data shows that the silicon SCI generally appears to be reversible on the first cycle in the ethylene carbonate containing electrolyte. But with the addition of the electrolyte additive fluoroethylene carbonate, the SCI becomes much more robust and irreversible. And to just graphically summarize this study here, we can see that during the lithiation of silicon in an EC containing electrolyte, we form an electrolyte an SCI that's going to be very rich in lithium oxides, along with organic carbonates coming from the ethylene carbonate reduction, which is generally thought to produce a compound called LEDC, or lithium ethylene dicarbonate. But on the first delithiation, so the first discharge of the anode, this LEDC component is actually going to be oxidized on the silicon surface, and it's going to be unstable for the silicon passivation. With the addition of fluoroethylene carbonate, or FeC, an electrolyte additive commonly thought to be very important for silicon stability, we're going to produce a completely different SCI chemistry. Instead, going to rapidly polymerize this FeC molecule into a poly-VC type polymer. And this poly-VC is going to be very stable on the silicon surface and going to be very robust against oxidation. And what this does is it provides very good passivation and good mechanical properties to the silicon surface. But what's also interesting is that this very irreversible SCI is going to seem to be reflected in that first cycle efficiency. So if we look back to that first cycle efficiency plot, we show that with the addition of FeC, the first cycle efficiency of the silicon anode generally goes down. And that's likely because that irreversible SCI is not giving back as much lithium on that first cycle, which might appear at first glance to be bad for the silicon anode, but it's reflecting the very good stability imparted by that SCI. And that brings us to the end of this work here. But of course, there are a lot of further questions that can be addressed with this very powerful tool of cryo-TEM. Of course, fluoroethylene carbonate, it's a very important additive, but it's not the only additive out there for silicon and lithium metal batteries. There are a lot of other additives that are very promising for making more stable silicon and lithium metal anodes. And using cryo-TEM, we can understand what they're doing within the battery SCI. For the silicon anode, this is only the first cycle of the SCI, or the first cycle of the anode, but the SCI is going to change dynamically as the battery goes out to the late cycle and end of life. So we also want to use cryo-TEM to study how the SCI is evolving through the late cycle and to the end of life of the battery. And these are all very good opportunities for cryo-TEM that those in the field should be pursuing, in my opinion. And lastly, I just want to acknowledge my advisor, Professor Yi Cui at Stanford, along with the various collaborators that helped with all of these works. And if you're interested in reading more about this field, cryo-TEM for batteries and just material science in general, these are a few suggested papers that I would recommend. These two works are those I described here. For lithium metal, there's a very good body of literature, both by our group and others in the field. And for just a general introduction to the field, these two review papers are very good resources. And if you have any questions that we don't address here, you can also reach out to me. This is my email here. So please send your questions into the questions panel here in GoTo, and I'll be happy to answer them now. Thank you.
Thank you very much, Will. Very nice presentation. We do have a few questions that came in. Let me start with, okay, for the high resolution TEM images, what kind of dose have you been using and what detector are you using for this work?
Yeah, so that's a great question. So in these two works here, those are taken using a one-view camera that we have here at Stanford. So one-view, which is it's a 4K by 4K CMOS type camera, but it's not a direct electron detector. So the dose that's required to obtain a high resolution image there is a bit higher than what you would get on a direct electron detector. So the dose used in those TEM images is on the order of 1,000, approximately 1,000 electrons per square angstrom.
Okay, thank you. The other question is, what is the advantage of the cryo holder that you used over previously used vacuum transfer holders?
Okay, yeah, that's a great question right there. So let's see if I can go back to that slide. So the cryo holder we use, it's a Gatan product. It's a Gatan 626. But the main advantage of a cryo holder is, firstly, a vacuum transfer holder, assuming that your vacuum transfer holder does maintain your sample at good vacuum, which is not necessarily a given. You don't truly know the vacuum that your sample is seeing and whether that's good enough to prevent oxidation. But if you assume that it is good enough and you get into the TEM column, you still have to deal with the beam damage issue. So if you can, in fact, transfer, say, lithium metal that's been protected from air reaction, you would not be able to get high resolution images because the lithium metal is still being beam damaged by the electron beam. But with the cryo holder, not only do you have very good corrosion resistance to your sample, simply because it's held at liquid nitrogen temperatures, and you're going to kinetically impede any oxidation or corrosion reactions. But once it's in the column, your sample is going to be stabilized at liquid nitrogen temperature, which is going to greatly reduce your mass loss and reduce your beam damage, which allows for high resolution imaging like that image shown here. So it's okay. Basically, the main advantage is going to be stabilization from beam damage, but you also have a little bit more you might have a little bit more confidence in the corrosion resistance as well.
Okay, next question. What other material systems can cryo-STEM be used for?
Yeah, thanks. So that's a good point. So here I talked mainly about battery materials, but of course, cryo-TEM has opportunities for any beam-sensitive material, along with any air-sensitive material. So in these review papers down here, they outline several other material systems beyond battery materials where cryo-TEM could be useful. Recently, it's been demonstrated of cryo-TEM for stabilizing metal organic frameworks, which are a inorganic-organic hybrid type material that's very beam sensitive, along with organic-inorganic hybrid perovskites used in solar cells. Those are two other recent works, but polymer materials are also very good applications of cryo-TEM, and there are many more. So I would direct you probably to this review paper here in ACS Nano, where we describe several other material systems that cryo-TEM could be used for.
Okay, maybe one more question. Within the battery field, do you envision cryo-EM to be used as a routine tool, or is it a more specialized characterization technique?
Yeah, so that's a good point. So that kind of also brings us back to what I was talking about earlier of this use of XPS as kind of the standard tool within the battery characterization field. So XPS, generally, most people do use that for characterization of the SEI within battery science. And it can get you pretty good information, but from what we showed here, it's not really giving you the correct structure. So cryo-TEM, it is a slightly more complicated tool. It's slightly less established than XPS within the field, but it provides a lot more richness of information for your study of the SEI. So I think, to me, I see cryo-TEM as something that could become a relatively high-end but very useful or more commonly used characterization of your SEI within the field. A TEM is not cheap. It is fairly expensive, especially one with analytical capabilities, such as a modern EELS detector or a direct electron detector camera. But it is still, and it's not something that every institution has, but it is still a relatively accessible instrument compared to, say, like a beamline. While it might cost more money there, it's easier to get time compared to like an X-ray beamline, which are commonly used for studies of cathode materials. So I see TEM, cryo-TEM, as laying somewhere in between that of XPS or SEM, which most institutions do have, and a beamline, of which there are only probably a few dozen in the world. So it's useful for high-end characterization of your SEI if you're really trying to understand what's happening within your SEI, the structure and chemistry of different components. But I do recognize it is less established than XPS and maybe less accessible to many institutions.
Okay, we have good questions coming in, so maybe I'll ask a couple more. One is, do you think cryo-EM in combination with low kV could be beneficial, like 30 or 60 kV maybe, for this type of work?
Yeah, thank you. That's an interesting point. So in the structural biology field, low kV microscopes are very desirable because they are lower cost and they also can produce higher contrast, but they are also generally thought of to be as more damaging to the specimen, from my understanding. So the effect of the microscope accelerating voltage and whether or not that improve and its effect on the degree of beam damage to the sample is quite complicated. Ray Egerton has a few review papers on this topic, but basically going to lower kV does not always just monotonically decrease the amount of beam damage. For materials where you're sensitive to primarily sputtering or knock-on damage, such as graphene or 2D materials, low kV generally is thought to be as a good thing. But what we found for lithium-based battery materials is that you actually get more beam damage at lower accelerating voltages. And actually, at 300 kV accelerating voltage, we found there to be the least amount of damage to lithium metal. And this has also been described in a paper in ACS Nano. I don't remember the exact reference exactly, but basically they found that the scattering cross-section of lithium is actually, or the damage cross-section is lowest at higher accelerating voltages. So for cryo-TEM of battery materials, you might actually be better off with a higher accelerating voltage. But for other systems, it may differ as well.
Yeah. Okay, thank you. This one is the last one. Have you tried using direct electron detectors like K2 and K3 and dose fractionation for imaging lithium battery materials?
Yeah, that's a great question, and I kind of hinted at that earlier. But direct electron detectors, such as the K2 and K3 by Gatan, along with other offerings from other companies, those are going to be very important for the low dose characterization of the battery material and its SCI. So we do have a K3IS recently installed at Stanford on our analytical microscope. We've done some work characterizing different battery materials using the K3IS with low dose, and there should be some interesting work coming out soon from Stanford looking at those materials with the dose fractionation capabilities on the K3IS.
Okay, I think that's all I got for now. Thank you everyone for attending the webinar and submitting your questions. And thank you again, Will, for your time and a very nice presentation. And I wish everyone a great day. Stay safe and healthy.
Thank you, Anna.
Thanks. Bye.